So welcome to this workshop this afternoon. It's a workshop. We will do some mental exercising. My name is Vlad, like Dracula. Here is Peter. And Peter is a specialist in color science, and Vlad is a specialist in shape analysis. This is our difference, and we will put it together and have a dialogue between the two disciplines, and also a dialogue with you, because we expect you to have questions. So how will it work, and what is it about? So it is about color, but everybody here is interested into shapes, right? So normally we should not be interested into color, just shapes. And our talk here, our workshop here, is to show you why color is interesting if you do shape analysis, right? So this is the goal. Now, how are we going to do it? Everything evolves around pictures, right? Pictures is shape and color. So I will present the pictures, and you will show some phenomena, something interesting. And then I ask Professor Color Science, what is a phenomena, to explain it? Why is it so? And at the end, I will say 2 words why this is interesting for shape analysis, the color phenomena, okay? So we can start right now with such a phenomena. We have 1 hour, so that you know. You can, everybody is seeing here the number on the screens, the number 18? No. 8 maybe? Does anybody see another number than 8? Oh, it's a pity, because...
There are more than 10 men here.
Yes, that's
it's a question you shouldn't ask.
So there are some people that would see here the number 3. Why is it so, Peter?
Yeah, I mean, it's a typical experiment which demonstrates how, let's say, limited our visual system is. We have 2 types of sensors on our retina, and we have the cones and the rods, and one of those types is sensitive for illumination when we have very dim light, and the other is working when we have a lot of light. So there, when we have a lot of light, we have 3 types of receptors. One is sensitive to red colors, another one to green, and the third to blue. And you can imagine those sensors like absorbing small elements, and they are filled with pigments. It's called opsine, and those pigments, they can be faulty. So it means the receptors which are sensitive to red, they absorb red light, can be filled with the opsine, the pigment of the green cones. And if this is happening, we cannot distinguish between red and green colors. So we call it also colorblindness. And this is a typical example. We have there actually 3 different colors which are not very clearly visible on this beamer. We have the number 3, which is much more reddish than the left part of the 8, which is a little bit more orange, and we have the background in green colors. And this is a typical experiment to see if a person has a red-green blindness effect, because one of the cones is not filled with the proper pigment. So that's a very simple example. And as you mentioned, correct, we have more than 10 men in here. And this is a typical problem. If you are male, there is a big chance that you have this problem with wrong opsines. And this is not really an issue. You can get used to it. Besides, if you want to get to become an electrician, it's essential that you know which wire has which color. Or, for example, a pilot or locomotive pilot.
And the advantages to this Daltonian, what is it? In French, they have a term that's neutral. They don't say.
Oh, yes, exactly. Yes, exactly. Yeah.
But to find camouflage, they choose people.
Yes. Yeah.
So you imagine that also paleographer, if they have to deal with color images, they might have these problems of deciding, is this 8 or 3 that I see there, right? But not only paleographers, also computer scientists. Imagine you want to do a software that is reading 8 and 3, so you have to design it. So this is the Ishihara test. It's called the Ishihara test in optometry. And it's a good example of something that, a pattern that you cannot process as shape without color information, right? I will give you other examples. Here, for example, for the computer scientist, imagine you want to do character spotting. How many E's are there? Huh? 6, maybe 5. I have trouble deciding, right? But how about this? Isn't this much easier to do? So, another example here, texture segmentation. On the right side is a bit more difficult than on the left side to do texture segmentation, right? Okay, so these are examples so that we try to make you understand that there is a good utility in looking at color when you do shape analysis. Good. So now we are going into the res materia, and we start with color science. Here is what color science is. All these different things, starting from electromagnetical, material, the imaging hardware, color processing, displays. We all have here displays. Psychology, because we have eyes and look at these images, and also culture. All these different things and different disciplines are involved in the study of color. This is color science. So it's fantastic because everybody can participate, right? So what we are going to look at today, because we have limited time, we are going to look at 3 different things. One is color space, a color space. Then something called Gamut mapping. And the third one are the color spaces again. So twice color space, 1 gamut mapping. And what is a color space, Peter? Can you explain us?
Yes, I would like to, we can look here at 3 examples how we can interpret color. And what you see there, it's always something which has 3 components. And as I explained earlier, we have those 3 types of color-sensitive receptors. And so we can live quite easily with those 3 components. And the amazing thing is that our eye is able to create the full spectral amount of visual impressions of colors as we know it from the rainbow, just based on those 3 components. And we have here a blue component. This is the sensitivity of our blue cones. We can put this on top of it. We have here a green component, and if we put this on top, we have all colors of the rainbow. And that's really fantastic. I mean, it's not something which is immediately clear that it works so fine, but our visual system, and the eye is a part of our brain, actually the retina, is really capable to do that. And so it means for most things we are looking at, we can work and live with 3 components. Usually, if we speak about computer systems or cameras, we use red, green, and blue without a more detailed specification, which is quite important, as we will see later on in color spaces. But actually, this is a very heavy limitation because, as you know, light is something which has full spectral power distribution, which means it has all different types of wavelength. It's an electromagnetic energy which we perceive. And the visual range of these electromagnetic waves is between about 400 to 700 nanometers. Something which is down at 400 nanometers, 450 nanometers, we see as blue. Stuff which is around 550 nanometers we see as green, and stuff around 650 nanometers we see as red. So 450 blue, 550 green, 650 red. Below this we say it's ultraviolet. We don't see that, but we can measure it. Above it we see infrared. We don't see this, but we feel it as warmth. So that this strong limitation is something which we are working with in nearly all technical implementations of monitor screens, mobile devices, cameras, not of course in special imaging techniques like multispectral cameras, but what we see here is now that we are also able, or that we mostly improve our free components, so our coordinate system, according to the application we use it. On the left we see RGB. RGB are the free components of a typical monitor. We have for each pixel 3 points, a small red, a small green, a small blue one. And as you have seen in the Photoshop example, if they are close enough together, we see all possible colors. The other one which I would like to mention are the two in the middle, especially the YCB-CR color space is something where we try to separate luminance from chrominance. So in RGB we have 3 color components, red, green and blue, but our brain, not our retina, but our brain and our perceptive system is not sensitive to red, green, blue, but to something which we call brightness or luminance and something which we call chrominance. Interesting is also that if you ask people what basic fundamental color they can see, it's not red, green, blue, it's red, green, blue and yellow. So we have like 2 axes, red, green, blue, yellow. Those are completely complementary colors. There is nothing like a yellowish blue. It's not existing, or a greenish red. So those are 2 components, and the luminance is the third component. So what we see there, YCB-CR is a color space which they created in the world of video and broadcasting, especially video. Because what is interesting, when they moved from black and white to color broadcasting information, they needed to be compatible with the old systems, but they needed to add color information. And due to the fact that our visual system is capable to really interpret completely different kinds of incense, this works for us as well, and what we have there is Y is the luminance, CB is one color axis, it's the red-greenish one, and CR is the other one. And what we can see there is something quite interesting. You see there like points, it's quite far away, but there is like a grid. Those points are like a little bit more segmented than in the other color space, and the reason is for the, thank you. You see it here. Those lines. It's not a completely full volume. Here we have a full volume, there not. And the reason why this is that we are not very much sensitive to resolution in color spaces. So you can actually get rid of half of the information and we still see a completely sharp image. That's extremely helpful, for example, in video broadcasting. You don't have to use a lot of bandwidth. You can transmit a color image without a lot of color information. For data analytics, this of course is really essential because we only have to have resolution, so we don't have detailed information. Another thing which I want to show on the right, it's this one here, it's called LAB. LAB is a color space which is actually representing the standard human being. It's the standard for how a person sees colors. The interesting thing is it's a completely well-established standard. Each and every computer is using it. It is actually based on 49 British men, which were examined once in the 40s and once in the 50s. So it's completely not correct type of standard. And just even in this data of the 49 British men, in the red component of this experiment, we have about 25% of scattering. So if we too see a color, it is absolutely likely that you think it's something which is greenish and I say no, it's blue. And both are right because we don't see the same thing. And LAB is interesting because it's really a standard which is everywhere, but it needs to be just known that it is not something which is really the truth. It's not something like ground truth.
So what I see here, Peter, is what you said, volume. You see these are volumes. But these volumes here, the bodies, right, they can be smaller and bigger. And this is what defines a color gamut. Gamut comes from musicology. It's a scale, you know, gamut. So it's a volume. How much big is this volume? Now, what is a color gamut? Can you show us a color gamut closer?
Yes.
Because these are like between 0 and 1. It's normal.
You see here on this slide, actually, and I can even open it on my computer. Color sync.
Oh.
Okay. So, due to the fact that we have 3 components, we can actually span a space. And those 3 components, in this example, it's the LAB plot. It's something which here has a certain size. So it means the gamut shows or demonstrates all possible colors which can exist or which you can reproduce with a specific system. So if we have a color gamut like we see it here, and those are 2 color gamuts, one is larger, the grayish one, the other is smaller, it's the colored one, you see that the color gamuts are not always the same big. Why is this like this? The reason is, as you can imagine, if we take 2 monitor screens and we say both work with RGB, both have a specific red, a specific green, and a specific blue. It's actually the filter which is on top of this screen. It makes the pixel looking colorful. The backlight is white, and then you have this filter. And it depends now on the specific material which is used on the specific filter, and due to that filter, you have either the possibility to visualize more colorant colors or less, and this defines also the size of this color space. So it contains all possible colors a device can either capture or visualize.
And when Peter is saying all the colors, that's interesting because it means colors of our computers, colors of our display devices, but also the colors perceived by the human eye, by the human eyes, right? And here we see what do we see?
Actually, it's a very simplified visualization of the 3D space, which is called XYZ. You have to imagine when they wanted to find out how is the standard observer actually seeing colors, they started with red, green, blue experiment. And the experiment was very trivial. They showed the color and they said to those 49 British men, you have red, green and blue lamps, mix as long as the reference and the target color do match. It's therefore called color matching experiment. And what they found out is that this is not possible for all possible colors of the rainbow. There are specific colors where you would need to have a negative red to find a color match, and this is not possible. What they found out is it's a linear space, this RGB color space, and due to that we can do any base transformation, and we do a base transformation so that we only have positive values, and so that nobody believes those are real colors, we call it XYZ. That's what this slide shows, but it's only the cut through this XYZ gamut so that we have a plane, a standard plane. And in this plane you see 2 different color spaces. One is called Adobe RGB. It's a standard which Adobe created. It's a this triangle which you see is white, and the other is a gamut of, for example, just a document you would like to capture or to plot. And you see they do not match completely. So the Adobe RGB color space is only able to reproduce about a third of all the colors a standard observer can see, but it's also not able to reproduce all the colors which are within this press gamut. So we have a dilemma. What do we do with the colors which are in the original, but we cannot reproduce it with a color space?
And this has a direct impact on something that paleographers are doing, which is reading. Now, what's the impact? Here, what we see here is the same document, once on the right in Srgb color space, and no, I need that image.
Oh, sorry.
So this is original on the right, the original Srgb color space, in which the image was imagined by a scanner, right? On the left is Adobe RGB. So we took this as Srgb and opened it in another space that is not the real original color space. But what do we achieve by that? We boost the color contrast, the chromaticity contrast. And by that, we are able to read it better, to have better legibility, right?
Maybe as an explanation, what means sRGB and Adobe RGB? You have to imagine in the early times of computer technique, where computers were quite slow and not able to really calculate different color transforms, they had just 3 components, a red, a green, and a blue component, and those 3 values were sent to a graphics card and displayed on a standard screen. And the classical standard screen, the big things with the beams in back and the front 3 filter arrays, they had a very typical and specific red, a very typical green, and a very typical blue. So that you can say all those screens are more or less the same, and these 3 colors, they span a color space which is called sRGB. This used to be standard for many, many years, and if you don't do anything with your computer about color management, most colors are interpreted as sRGB. This is quite okay. It's not a huge gamut, but it's okay. And to overcome this, Adobe said, we are the imaging company. We need something which is bigger, and it must be especially very different than what Microsoft is doing, because sRGB used to be used by Microsoft very hardly. Adobe said we need something bigger, and they did Adobe RGB. And what I would like to show you here quickly, if I go again to Photoshop, and I zoom in a little bit the image so that you see it here, then I can actually change meta information. Maybe I make it a little bit bigger, like this, so that you see it. And now I have a meta information which tells me what kind of color represents my RGB image. And if I say sRGB, it looks like this because it is an sRGB image, but now I have hundreds of different RGB color definitions. Each and every camera has its own RGB definition. Each and every printer has kind of its own RGB definition, also screens. And if I change just this meta information about the meaning of the RGB values, an image can look like this. I didn't change anything on the data, it's just the information about what do they mean, those RGB values. And therefore, RGB doesn't exist. It is not something which means anything. You need to be very precise what RGB is meant, and sRGB is just the standard which is usually used and interpreted if you don't define anything more. If you have a not well-defined image, it's usually interpreted as sRGB. Browsers work like this, email programs work like this, it's everywhere.
So what did Peter do right now when he changed that information? He did something called, as I said before, the Gamut mapping. You saw you have 2 spaces, And what Peter did is transforms the data from one space to another one. And here is an example what that means. You have points in space, and you reduce that space. So the distribution of your data, the numbers that you have in that image, change completely. You started with 100, and then you end up with 73, right? So every time you open an image and you save it and you change your color space, that's what you do. You can completely change your data. And here are two gamut mapping techniques.
Yeah. So, I mean, the typical example, what you could see there is, imagine you have an image which has, it's quite rich, it has quite saturated colors. I mean, on this chromacity diagram, this plane are on the edge. Of course, it's the beamer, it's not the truth of the nature, but on the edge, you would have all the colors of the rainbow. So the most saturated and purest colors that exist. Purest color means actually only one wavelength. So just one value of nanometers. It's not, there is no other color mixed in. It's very super precise and super clean. And so what is also interesting, that's why we have a line down there, because there is no single wavelength which makes the mixture of red and blue, because in the spectra, red is on this side and blue on this side. So that's why we have this line there. It's also called the purpur line. And what we see in this gamut is that the white triangle is able to display much more, or to represent much more saturated colors. And now you would like to go to a device which has a smaller gamut. For example, a screen like this, which has usually sRGB. So what do you do with all the white points which are outside of the destination color space? That's a problem. It's really a problem, because there are completely different applications. If you want to have just the most saturated colors because you need it for a graphic or to display like a bar graph, you do more something like the Gamut clipping on the right side, because you say, I'm not really interested about this very specific difference in single colors. But if you want to do this with a photograph where single colors are essential and to distinguish two colors which are just a little bit different, you do something which is more on the left. It's called, written there, gamut compression, or it's called perceptual gamut mapping. So you try to squeeze the whole larger gamut so that it fits completely into the smaller volume, but you don't do this on a very trivial way. It's a highly complex mathematics. You try to do it so that the visual impression still looks good. And usually your computer system is doing this on the fly. It's part of the color management system. Here it's even being done twice. I have my source color space, which is represented by the file. Once on the fly, the data is converted for the screen, and in the other way, it's converted for the beamer. So this is really one of the major issues, or the major things which a color management system in a computer is doing. And this is also something, if you get data like in the gamut clipping case, you of course lose a lot of information. It's not there anymore. It's just as clipping says, you don't have as much as you had before. And this is something which is a very problematic thing. You don't know it. So if you get a file which has been color processed and where gamut mapping has been applied, you don't know which one has been applied. You don't see it in the data, and that's really, it's something which is quite important to know, because that's also a reason why you should stay with image data in as big color space as possible. And sRGB is always not perfect for that thing, because it is small and it is just perfect for display on a screen, but definitely not for any kind of data analytics.
And this has a repercussion on the images that you are looking at, that you are processing as a computer scientist. And here are images about that. This is what the result of what we talk right now. You have these two papyri, the same papyri, taken at the same institution, but at different times, by different people with different hardware, you see the result. They don't look the same. And we have barely any information inside, right? Now, this has also, not just looking at it, because maybe you don't care about the colors, but you care if you do defragmentation, right? You would like to have the same color put together like in a puzzle. Is this possible? What can you do when you have such a problem?
It's quite an interesting point which gets more and more important. I don't know if you have heard of the IIIF consortium. And IIIF, actually the International Image Interoperability Framework, would like to make it possible so that you can easily combine different image sources from different repositories in one, for example, web application. So you get, for example, one fragment from there, from Paris, another fragment from Berlin, and you merge them in the same web environment. You have a standardized interface so that you can bring this data together. But if you do this, it's getting essential that you know how this data was created. And that's something which is still a little bit like orthogonal to all those efforts to merge data from different institutions and to be interoperable, even though there are very strong processes in standardization of image capture. In the United States, the most important is FACI. It's the Federal Agency for Digitization of something. I don't know exactly what it means. But it's a standard which defines what processes do you have to do so that you get good and more or less valueful image data. Then we have in Europe another standard which is called Metamorphosis, and it explains you how you have to calibrate the camera, how you have to do Gamut transforms, how you have to save your data so that you get something which is reproducible and which has valueful data. And something like in this example should then actually not happen anymore. The problem is a little bit that many institutions, even larger institutions, just say, okay, we have a system, it's digitizing our originals, we don't really exactly know what is happening in there, and we get a file which is coming out which we don't really know what it means, what is in there. Just an example. There is a strong trend from the large companies, especially Adobe, that even image data is stored in PDF files. So if you buy a closed system, a box, you scan images, originals, and you store a file, you get a PDF which you don't know what it actually means. And Adobe is clearly on this track to say, TIFF, for example, we don't need it anymore. PDF can do the same, and they don't distinguish between document and image files. So it's really important that you have rich metadata about the image capture is in TIFF files and other formats majorly called EXIF data. It's technical meta information about the capturing devices, that you have information about the color spaces, and that you check that you keep those meta information. We have a lot of programs, got to know, which do automatic file conversion. Trivial stuff, even just changing something like the author information in the Dublin core metadata, which had the consequence that, for example, EXIF metadata was completely deleted. Because what happens, you read the file, you process it, and you write it again, but you don't take everything into account. And that's really a big problem if you have large data repositories where you need to migrate. Be very, very careful that you have as much meta information about your images as possible, and check that you keep it.
And this is something we all do, the computer scientists. I worked with MATLAB to do image processing here, and MATLAB is not taking into account the color space, it's not saving the color space. So I had to do quite a lot of research how to incorporate and use color spaces with MATLAB, which is something that a lot of people are using. So you see that, and you are not aware because it's just a line to transform, from RGB to LRB, and then it's okay, it's there. But in fact, what happens? Everything changes. So we move now to another topic. We have a number of topics like this, which is another example where color is indispensable. You work with color when you work with shapes. This is multispectral images. Now I will describe you what the difference is between the images. VL, so northwest, that's visible light. That's how.
Could you make it full screen? Can make it a little bit bigger. It's
get rid of the bar on the right
Yeah.
here.
The problem is if I do full screen, it crops a little bit down there. I mean, we can try.
Yeah, we can try.
Like this.
Okay, so VL, that's northwest, that's visible light. That's how you see, your eye will see this papyrus, okay? That one, the next one, IR, is infrared. So that's something that you cannot see with your eye. But there are machines that can photograph that information. So you see there is a difference between these things, right? So this is called multispectral because you have different slices in the color spaces that you can use. Now, you see that there's a difference. So we want to take advantage of the full information that is available there. So one simple thing that you can do is just to colorize your infrared with the color component of the visible light, which is southwest image. So suddenly it's better. It's better than maybe or more familiar than looking at the infrared image, which is monochrome, right? There are other techniques. You can improve it with decorrelation, for example, that colorful image down in the middle. Again, you can colorize it, and you can get something which is familiar to you as a paleographer or as a human being, right? So what can you tell us other about multispectral images?
Yeah, I mean, it's...
There is also fusion. We heard about fusion.
Yes, I mean, it's unfortunately it's not something which you can do easily because, as you said, you need specific hardware. I mean, the light source is not really the problem. We have always the full spectral information in most light sources. But you need, for example, to capture infrared reflectance photography, a specific camera which is measuring infrared information. A chip, as it is built in a digital camera, is usually super highly sensitive to infrared information, but to not interfere with the RGB colors, you have an infrared blocking filter in front of the chip. And so it removes all the interesting information of infrared, and you need to remove it. And that's not something... Actually, we did it, we tried it, the camera still works, so you really have to break it, and then you have full infrared sensitivity. And the infrared sensitivity is about twice as big as the RGB sensitivity, so it's for example, there are like Sony video cameras, they have this night vision mode. Night vision is just removing the infrared blocking filter. So that's very nice. And then you get, of course, much more information about stuff we just don't see, because as we have seen earlier in one of the slides, our visual system is very highly limited, and we are just staying with the RGB information. And if we get more information about reflectance, or even maybe not for this originals, but stuff like UV fluorescence, where you induce UV light and the material reflects in the visual range, is highly interesting to make things visible which we usually cannot see with our eyes. And that's just an example of how you can improve even structures on the original by such techniques.
Yeah, or imagine you have metallized colors, like on cars, metallized. That's another layer that you could add to a color than RGB. You have that metallized thing. And that's information that you can add in the metallized layer, or other layers, sparkling things, you know. So that's interesting. You could have more than 3 layers, actually, than RGB, which you could process. Now, the next image here, the next case study, shows you again something that is usually done when you want to read a document, enhancing of the image. On the left, far left, you see the original image as it comes, and it's a bit difficult, it's dark, so then you have to enhance the legibility. Now, there are many different ways in which to enhance legibility. We present here 3 different techniques. The first one is done in the color space. The second one is enhancement local contrast in lightness only, so no color space. And the last one is the Retinex method. Now, Retinex, you know, everybody knows about Retinex, even if you didn't hear about the word Retinex, because you know the Polaroid. The Polaroid camera was invented by Land, and Land invented also this procedure called Retinex in order to improve the legibility of images. But for paleographers, look at the result. It enhances both writing and the structure of the papyrus. That's not something you want to do. So this is why the second image from the left, which we developed here, enhances only the script, or mostly the script, right? So this is what we see here. Maybe you can tell something else.
Yeah, I mean, it's of course we are in a 3-dimensional mathematical space if we work with the 3 components, and you can do so many different things that it is actually worth to adopt the methods you are applying to the data to the thing you would like to get out. So there is nothing like just the one true process. Maybe someone is more interested in one of the 2 more right results, depending on the application.
Now, the next image here is about the file formats that Peter mentioned, TIFF, JPEG, and other formats. And here what we see is on the left, the image in TIFF format, then JPEG format at 100% quality, that's compression, and then 10% quality. Now, quality means you compress the data, so you get less data, less information. You see, from far away, there's little difference between these different formats. But when you zoom into it, you see on the right, the JPEG, it's destroying the structure, the shape. Right? Now, how come it destroys the shape?
Also, I mean, first of all, why do we need data compression? We have now still somehow this effect that people want to have more and more megapixels in their cameras. It's today easy to buy a camera with 150 megapixels. And there is something like an unwritten law that for image archiving, you use an uncompressed file format, which is as raw as possible, has as much color information in it as possible. And this is usually, or used to be, a TIFF file as 16-bit RGB data. And if you now take a 150 megapixel file and you have 3 components, each 16 bits, so 2 bytes, you get easily in the range of about 2 gigabytes for one file. That's problematic. I mean, even a super fast computer is somehow limited with this, and data compression also in archives is therefore an issue. Today, there are different formats, especially JPEG 2000, very popular because there are like fundamental things which a file format for archiving must fulfill. It must be as standardized as possible, widespread, and easy in operation. And JPEG 2000 is the most common file format now because each and every digital projection in a theater is a stream of JPEG 2000 files. It's called DCP, Digital Cinema Package, but it's there. So data compression is something which is important to store space, and it became very important in the context of the internet, where JPEG was like a phoenix. Because JPEG was not defined for the web, absolutely not. JPEG was defined for teletext and video text. I don't know, maybe some of you remember this. You have this button on a TV, and then it changes from an image of a TV show to text. And what they wanted to do is, before the web, to use video text as a channel to also promote stuff for marketing purposes, hotels, travels, and they needed a highly compressed file format for that, and this was JPEG. So it was never meant for computer applications and the web, but for video text. So what JPEG does are like multiple stages. First of all, it's transferring the data from RGB to luminance and chrominance. It gets rid of half of the chrominance information, and then it even goes a step further and it's converting the data from spatial information into frequency information, because the standard human being is not sensitive to different frequency in an image. A super high frequency means an edge from white to black. A very low frequency means, for example, the gradient in a blue sky. So what they do now is they get rid of all the information you usually don't see because it's not important. And what they did, because they had very limited processing power, they do this elimination of not really necessary frequency components in block sizes of 8 by 8 pixels. And this means that you do a specific elimination of frequencies for one block, and in the neighboring blocks you do the same process, but the result is a different one. And so you see this very clearly because, for example, very low frequencies, so just the plain color, can change from one block to another just due to the fact that based on the content of those frequency in this 8 by 8 block, you think this you can remove, and in the next block you say, I remove another thing. And this is what you see. That's a typical JPEG artifact, and one of the major drawbacks of JPEG, that it is only working on this 8 by 8 pixels. And so, as you can imagine, for data analytics, this is horrible, because a computer is super easily responding to hard edges. It's super high frequency information, and this is something you don't want to have. And therefore, don't use JPEG. That's just not good.
It's the same thing that I wanted to say. Thank you. Talking about frequencies, we have another example here. It's going way out of paleography. It's going into dynamics of airplane sound, the volume of sound. So that's information that you see on the top. That represents the sound of airplanes, like you would see next to an airport. On the lower part, you see the magnetic field of the Earth projected on a plane. That's the data. Now, why should we care about this? Because we will use some techniques like color bars, color mapping, to display those differences between the pixels, right? So on the left, you see a 3D representation, very nice. And then in the middle, you see something that is typically used, until very recently at least, the so-called rainbow color map. Now, what does the rainbow color map do with your data? Well, if you look at the magnetic field in the middle lower part, you see that red spot there. Well, that's not really there. It's an artifact. You think that there's a red spot, but if you look at the 3D representation, it's not really there and not so sharp. You see? So that's what the color map is doing with your data and with your interpretation of the data. Imagine as a paleographer, this would represent the eye tracing on a page as you read it, right? Well, you will interpret it in a totally different way that it really is. So now what can you do? Well, you use other types of color maps. You see there on northeast, that's a color map that varies only in lightness, right? So Peter told us about frequency. Lightness, we are sensitive to lightness in the high frequencies. Details. So you can see the details because the color map is working in lightness. Now, there are no details in the southeastern corner. There are only smooth transitions. Right? So then you use a different color map, which is changing in saturation. And then you see the data, much better than classified by rainbow color maps. All right?
It's absolutely essential that you like interpret information or enhance data in such a way that you make it most appropriate to the effect you would like to show and to the visual system. And I mean, this is of course a very complex thing, and I just would like to show you another, just something small on Photoshop, which is quite interesting, that we really have to distinguish between data and stuff we see. For example, if I have this image here, it's the Tower of Pisa, and I do quickly a copy of it, I place it in there, and now look now what happens if I move it over there. It's changing its angle. You see this? I do it again. I do it again. It's flipping to the left, although it's exactly the same image. So we have a very, very highly complex visual perceptive system, and it's also important. I mean, it's like a visual effect which is disturbing us, but you can also use stuff like this to make us more sensitive to very small details.
And this is something that I absolutely like it, and everybody should it's amazing, because this is about slant. Like slant. Everybody is doing slant, measuring slant. But there are different things of slants. There are physical slants that you can measure with a rule, right? Or perceptual slants. And what we see as humans, and when we write as humans, we do perceptual slant. So we would need to measure the perceptual slant, not the physical slant in our images.
Do you have a question? Yeah, if you compare, I mean, this is 3 times exactly the same image. So I just do a copy, and if you look at the visual appearance of the second tower, it looks like it's more going to the right than the first one, although it's exactly the same image. And there is another effect which demonstrates this very well. That's A and B looks like very different brightness, but if I copy a piece of A and move it to B, it's actually exactly the same brightness. You see, it's the same RGB data, although we believe that B is much brighter than A. It's not true in regards of the data, but we are used to the effect of a shadow, that a shadow dims colors, and that's why we see B brighter than A. So it's to distinguish perception and data, it's very important. It's no trick, it's not a program, it's Photoshop. No. Yes.
So we arrived at the end of our presentation, at least for our dialogue here. And we will end with something that you might recognize, and we will ask you to intervene. You saw that list of all the domains that color science is at the beginning of the talk. The last one was culture, right? So if I would ask Isabel to tell me, if I would say, okay, what color is that, is the sky? What color is sea and the dome? I would say blue. But Isabel, tell me in Greek, how does it sound?
As probably you may know, vocabulary of color is very difficult to translate in ancient Greek. So spontaneously I would say kyaneos, like cyan.
So it's interesting that there might be a difference.
Is that boros?
Another word.
Boros, is
You see? Oh, okay. So you see there are all already.
Blue, so if we want to call it blue, we call that. I think the sea might actually be chloros, which is kind of a greenish blue.
A greenish blue, a greenish blue. So if we give to ancient Greeks labeling images of the sea and the sky, they will label it maybe with green, and we will label them with blue. So imagine what the result is for your classification of images. You will end up with something like in the lower part where everything is green. Like in Homer, you know, Athena had glaucous eye. Now what is glaucous is? Glaucous is green, green and gray. But sometimes it's gray, sometimes it's green. Okay? So a computer will say, oh, this is green, so this is a prairie. We don't see a sea, we see the prairie. With horses, sea horses, prairie horses. Okay? So now we arrived at a cultural dimension of color science. Thank you, Peter.
Thank you, Vlad. No, that's it, actually.